Hi, welcome back to the second lecture. Today we're going to talk about random variables, and this is going to be the main thing that we'll be studying. In particular, for Markov processes, we're going to be looking at random variables that evolve over time. So they're going to have some dynamics to it. But in this lecture, for the probability review, we're just going to look at random variables and define them and see what we can do with them and look at the probability theory related to it. So for a random variable, I'm going to denote it typically by X, Y, capital letters. And the way that I think about it is going to be some measurement. And you can think about there being some noise or inaccuracy in the measurements, and that it's going to be a specific number, a specific outcome, but if you repeat the measurement many times, then it's not going to be necessarily the same. It's going to be within a certain range, within some confidence interval, and it's a random quantity of this measurement that you can make multiple times. So the idea for me, the way that I think about it is X, a random variable, is going to be a measurement. And technically, the way that we define it is through this definition here. It's kind of a lot, but it's not that bad. And what we need is that this X, this random variable, is going to be a map between two measurable spaces. So a measurable space, which is this and this measurable space, it's the same as a probability space, except that we don't include a probability function. And it's measurable because you could add a measure to it, which is the probability function, but we don't have to define one. So first we have that X is a map between measurable spaces, and more precisely, and we call this, and moreover, we have that X is a measurable map. And more precisely, what this means is that its X is a map between these two sets, these outcome spaces, omega 1 and omega 2. And additionally, we have the condition that if E is in the sigma field B2, then the inverse image of E under the map X also has to be in the sigma field B1. So this is a technicality to have to make sure that everything's consistent, so that if we can measure an event in B2, then the inverse image is also an event that we can measure. And again, this is a technicality, and for most cases, we're not going to worry about this second condition about having the inverse image be in the sigma field, because we're not really worrying too much about sigma fields in these courses. And the thing that I will remark is that continuous maps are always measurable, and you can have piecewise continuous, and you can even have something that's like a little bit more rough, and this will be measurable maps. And so for most applications, it's going to be clear that things are measurable, and really we're just going to worry about the fact that X is a map from omega 1 and omega 2. And so to recap, X is going to be a random variable if it's a map if we have a probability space, and X is a map between these two measurable spaces. So this is going to be a random variable. And again, what we're going to encounter in this course is that typically the target space for random variable is either going to be the integers, where the sigma field is just the power set of the integers, or the real numbers, where the sigma field is the Borel sigma field. And in those cases, we don't worry too much about trying to figure out if a map is measurable or not. Since most things are going to be like continuous, then it's going to be clear that is measurable. So this is the technical definition, and what, again, in the theme of the previous lecture, was that the most important object in the probability space is the probability function. And what we're going to do today in this lecture is that we're going to assign to every random variable a probability function that goes with it. And that probability function is what we're going to use to study the random variable. And so we're going to create, given a random variable, we're going to create a probability function. And that's how we're going to study random variables. So in here, this is just technicalities and making sure that everything's well defined, but we're not yet in a position where we can work with random variables. And we want to define a probability function so that we can do that. So this is what I call the induced probability function. So again, I have my random variable, and it's a map from this probability space to this measurable space. And you'll note that on the left-hand side, we have a probability function, but on the right-hand side, we don't. But we can use this map to define a probability function on this space right here, on this measurable space. And we do it as follows. We define what I call the induced probability function P sub x to be defined as follows. So if we have an event E on omega 2, and we want to measure it, take the probability of it, what we do is we take the inverse image under x. So we take E, and we look at the inverse image, which is going to be this blue region. And again, by the definition of a random variable, this has to be a measurable event. And then we use the probability of the function that we defined on the left-hand side to measure that event. So we define the probability P of x on the right-hand side. So we can add a probability function P of x, and it's an induced probability function by looking at the pre-image of events E on the omega 1 outcome space. And this is part of the reason why we want random variables to satisfy the second condition, that the pre-image of events is also an event. And in here, I denote the dependence of x by a subscript, so that this, if you have different random variables mapping these two spaces, then it's going to induce different probability functions. And in the following, you'll see this notation P sub x, and sometimes I'll introduce other notations to make it more clear, or rather, for convention, this is what people use in the literature. So this P of x, this is what we're going to do. This is what's going to have the probability information of this random variable. So let's continue. So again, for convention, this probability function induced by x is typically written shorthand as P that x is in E. So this x is in E, it really you should think about it as the pre-image of x. It's the pre-image of E under x. So what we have here is that this x in E really stands for this set, this event. And this is the pre-image of E under x, which is all the omegas in omega 1, such that x of omega is in E. So this is the pre-image. But the notation, the convention is to use this notation because this is a bit of a handful to write, and this looks neater. And in particular, when you look at the definition of the pre-image, you see that you can write it as this set where the condition is given as this. And so this is the important condition to determine the pre-image, and this is kind of what's written here. And additionally, people drop this omega to just make it a little bit neater. So in most of the literature, you'll see this type of notation, And it really stands for this kind of induced probability function. And it's what we use to study the random variable. And additionally, what we say is that if we have a random variable x, then the induced probability function, it's given the name of a distribution. And this is going to be the distribution of the random variable x. And this is going to be, and sometimes we'll use similar names. So, but the distribution function is really the probability function for x. And as I mentioned, we're going to have that the distribution function contains all the probability info of the random variable. And this is what is important, and this is what we need to study. So let me go through some examples. I'll work with I'll work through some discrete examples of some well-known and widely used distributions, and people we'll just name the name of the distribution, and then given the distribution, it essentially identifies the random variable, and then all the probability information you can obtain is from the distribution. But let's start a little bit general here. So here, I'm considering the discrete case where the target space is the integer line. So here, this is the target space, and this is the integer line. This is x mapping from an abstract omega 1. Here, this is omega 1 into the integers. And here, what I want to do in this example is figure out the probability of a specific event in omega 2 in the integers. So again, since the sigma field for the integers is all subsets, then a typical event is just going to be a subset of the integers, which is just going to be, for instance, n elements in n distinct elements in the integers. And for the induced probability function, what we want to do is figure out the probability of E, which is in this space. And here, using the shorthand notation, we really just write it as probability that X is in E. And using countable additivity, this is going back to lecture 1 to the defining properties of the probability function. We can actually write this as the probability as the sum of these probabilities. And again, this is a little bit more shorthand. This notation here, x equals j, x equals kj, really stands for x is in the event of a singleton kj. But again, we're trying to have easier notation, so we just write it this way. So we can just write it this way. And for any event E, we can just decompose it as the sum of these terms, where kj's are the different elements in E. So we see that from this example, we see that the distribution function of x is determined by some function x, p of x, p sub x, from the integers to 0, 1. And here, the way that p sub x is defined is that it's the induced probability function, it's the value of the induced probability function of the distribution at a single element x. So probability that x is equal to x. And this will be our distribution function for x in the discrete case. So it's going to be, again, it's going to be a map from the integers to 0, 1. And this is what's going to determine our probability function. And so with discrete random variables, the distribution of a discrete random variable is just going to be a map from the integers to 0, 1. And that's going to be it. And we do have the additional condition that we need to be careful about for this p of x. And it's really going to be that p sub x of x, if we add all the x's, that this is going to add up to 1. But this should be clear from the fact that the probability of the whole outcome space has to be add up to 1. And implicitly, by computing probability functions this way, or probabilities of the events this way, we're implicitly using the countable additivity condition. So it's kind of built into there. So this is the general idea, the kind of general setting, and now let's look at some specific examples. So the first example is the Bernoulli distribution. And here, the way that it's denoted when for certain distributions, for especially the well-known distributions, you're going to write that x little tilde Bernoulli p. So in here, this notation is telling you that x, the probability distribution of x is given by the Bernoulli distribution. And here, the Bernoulli distribution has a parameter p. But the interpretation of this is that x is going to either equal 1 or 0 if a coin flip is heads or tails. So a Bernoulli random variable is a random variable that really takes on two values, 0 and 1. Sometimes you'll see 1 and minus 1, but really the characteristic property of Bernoulli random variables is that it takes on two values. And you can think about it as a coin flip. So the probability of a coin flip. And in here, you can think of omega 1, the space from the domain of x is going to be mapping to 0 and 1. So in here, I forgot to, I have a blank space. Probably have a blank space. I'm going to add it to be this. So in here, the omega 1, it could really literally be anything. And it's when you flip a coin, it could be like all the things that can influence the coin flip. Maybe it's windy and it's just like the universe, and or maybe there's you flip it really fast, but this somehow abstractly encodes all the possible initial conditions of your coin flip and anything that influences the coin flip. But regardless of what omega 1 is, the domain of the outcome space, when you flip a coin, you only have two possible outcomes. It's either heads or tails. So whatever the initial conditions are, it's gonna get partitioned into two sections. The initial conditions that are gonna give you a tails, or the initial conditions that are gonna give you heads. And in particular, this is sort of a black box. We can't really like determine exactly what it is, but we could kind of give it a certain probability to it. So in here, the way that it works, if you look at the pre-image of 0, then it's going to be some region in the original space. If you look at the pre-image of 1, it's going to be some region in the original space, and it's going to be partitioned into two things. And the probability distribution, again, is going to be the induced probability function of x, which is just the probability of the event x equals 0. And in here, the event x equals 0, we look at the pre-image of this. And it's going to be this region. And this is where the probability function is actually defined on this initial condition space, or this outcome space. But whatever, so if we look at the pre-image, it's going to be the probability of this region. So it's going to be the probability of this, which is just going to be some number between 0 and 1. And we're used to coins being fair typically, and so a lot of times you'll see this to be 1/2, but really you can have a biased coin, and this is a parameter of this Bernoulli distribution. So we write it Bernoulli P. And in particular, you can do the same thing for P sub x equals 1, or P sub x of 1, and we see that the Bernoulli distribution is defined this way. For x equals 0 equals P, and for x equals 1 is equal to 1 minus P. But actually, I think the convention really is that if we think of 1 to be heads, to be a success, we think heads to be success, then this really should be this way, conventionally. And then this would be this, and then this should be this. And here, I want to switch this. So 1, 1, and 0. So again, the probability distribution for x is just going to be a map from the integers to 0 and 1, such that all the integers add up to 1. And here, that's what we have. This is going to add up to 1, and this is going to be 0. So this is the Bernoulli distribution. Let's move on to the next distribution, the binomial distribution. And we have two parameters, n and p. And actually, I Wikipedia'd this. I forgot what's the way that people denote this, but in here, you'll see that if x has the binomial distribution, then it's going to be denoted by this, with this squiggly. And the interpretation of this random variable is that it's equal to the number of heads in n coin flips. And this is a common theme for random variables, that people like to associate a random variable with a thought experiment, and then they can kind of like use that interpretation to inform the probability theory coming from it. And so, but it extends to other situations. And what people like to do is they have a random variable, and then somehow by analyzing or thinking about it, they can make a connection to, say, coin flipping, and then they're like, oh, this is just like coin flipping, and then they understand it that way, and then they can inform their probability theory that way. So it's kind of like trying to go back and just like simplify the problem and just abstract it to like the simplest things. And a lot of times it's just coin flipping. So in here, for the binomial random variable, we have coin flip. We're flipping n coins, and we're counting the number of heads. So in here, again, the possible outcomes in the integer line are going to be these outcomes. You get 0 heads, 1 head, and all the way to n minus 1 and n. And if you look at the pre-image of this, each of these events, it's going to partition your original outcome space into n plus 1 subsections. So we have, this is the event at x equals 0, this is x equals 1, all the way to x equals n. Then for the probability function here, the induced probability function, or the distribution here, this is actually going to be defined by this formula, which is n choose k, p to the k times 1 minus p to the n minus k, 0, 0, where k is between 0 and n, which is the possible number of heads. And otherwise, it's going to be 0. And here, this is a combinatorial term, n choose k, which is equal to n factorial over k factorial n minus k factorial. I assume that you're familiar with this formula, which you've seen in other contexts before, and that you've seen this argument that if you have this n coin flips, then this is going to be the appropriate probability function. And additionally, this is if you set n equals to 1, that's one coin flip, and we're back to the Bernoulli distribution, and we have that in this case that it's going to be p of xk. It's going to be 1 choose 1, or 1 choose k, p to the k, 1 minus p, 1 minus k. And this is for k 0 or 1, and then 0 otherwise. And this is equal to the Bernoulli. This was the Bernoulli distribution. And so this is consistent. So you can think of the binomial distribution as a generalization of the Bernoulli distribution. And again, this is the reason why I switched the p and 1 minus p, because success ahead is interpreted with probability p. All right, so this is the binomial distribution. Let's keep going on. The next distribution to think about is rolling a die. And this is the uniform distribution. And we have one parameter, capital N here. And in here, we have x has the uniform distribution, which is denoted by this. You could, I guess, potentially say something like this. And that should be clear. But the way to think about this is that x, this random variable, is going to be the outcome of a roll of an n-sided dice. Die? Let's double down, die. And in here, the possible outcomes are going to be 1 through n after you roll the die. And if you look at the pre-image of this events over here in the original outcome space, then you're going to see that we're going to partition the outcome space into n sections. And here, we're going to see that the probability distribution is just going to be 1 over n for all the k in here, meaning that each outcome is equally likely, and it's going to be 0 otherwise. And in here, I think this is the, we have one more example. This example, so I'm kind of going through them a little bit quick. I've assumed that you've seen them in passing, but I just want to make sure you have them, and that we set up notation and we set up probability functions that we can just recall during the lectures, and we have what they are. And this last distribution that I'm going to talk about in the discrete case is the geometric distribution. And here we have a parameter p, and we have that x has the geometric distribution, and we denote it this way. And this is going to be interpreted as the number of coin flips it takes until you first land a heads. And here, in theory, you could potentially just get tails for an infinite amount of time. You can keep flipping that coin and never get tails. The probability is going to get increasingly small. So for that to actually happen, you need to do this type of trials a lot of times. But nonetheless, potentially you can go arbitrary a large number of coin flips before you get a heads. So the possible outcomes here are going to be 1 through infinity. So it's going to be 1, 2, 3. And if you look at the pre-image of this outcomes, it's going to partition your original outcome space, omega 1, into an infinite number of events. And really, in here, if we have this interpretation that it's less and less likely, then as the number, as x equals k and k is getting larger, then the slices are going to get smaller and smaller and smaller. And these are going to be relatively bigger slices. And that would denote that the probability of taking too many flips to get the heads is getting smaller and smaller. So in here, the probability distribution, this p sub x of k, is going to be given by this. And really it means that the first k minus 1, so if in this case p equals x, p of x equals k, that means that it takes you k coin flips to get to a heads. So that means that k minus 1 coin flips, the first k minus 1s are tails, and this happens with this probability. And then the last coin flip is p. So this is going to be the distribution function, and this is the interpretation. So we've gone through some examples in the discrete case, and just these are widely known distributions, and you should be comfortable with these distributions and kind of be able to work with them. And so this is one reason why I'm going through them, so that you're aware of them, but I suspect that you've already seen them before. Additionally, the other reason why I'm going through them is because I want to bring out this point that whenever we're working with random variables, it's the original the original outcome space. It's not playing that big of a role anymore. It's kind of an abstraction. It's kind of just like signifies the initial conditions of our measurement, which we kind of black box them or just think of them abstractly, but it's not really playing a major role in the probability theory of the random variable. What plays a bigger role is the range space, the outcome after the measurement. This is what you want to know when you make your measurement. This is what you're interested in, the outcome of your measurement. And additionally, the major part of the theory revolves around the probability distribution. And this is again where all the probability information is contained. And whenever we're defining random variables or working with random variables, we're going to say that x has geometric distribution. And what we want to think immediately is that this function, so that if we want to compute probability of an event with x that is geometrically distributed, then we're going to use this probability function to compute that probability. So this is going to be what we're going to use. So whenever we have random variables, we want to know what their distribution is, and then once we have its distribution, then we can compute probabilities. So here, the part of the reason of this examples is to showcase that the probability function is what's most important here. Now, let me move on to the continuous case. So we've been working with, before we were working with the target space, that was the integers. Now I'm working with the target space being the real numbers. And in here, again, events are generated by open intervals. So I'm going to try to compute, I want to compute the probability of an event AB. And what I do, again, to compute the probability of this event AB, I first take the inverse image under X, and I go here. This is one. I take the inverse image, and here I have a probability function that's defined in this original space. I have a probability function here, and I compute the probability of this pre-image here, and then I want to mimic what I did for the discrete space, where I can decompose any event, any set, into singletons, so specific values that X can take. But here in the continuous case, for any interval, there's going to be a countably infinite number of elements in there. In the discrete case, I can just really break it up into each element in there. But here, for the continuous case, I can't break it up into each individual event. But what I can do is I can actually break it up into smaller open intervals and write A as a union of smaller intervals. So in here, to compute the probability of AB, I can actually look at smaller intervals, this interval, and then look at its pre-image here. And in here, I just write this probability of this, that X is in this interval, as the sum that the X is in this in this smaller interval and add over all the smaller intervals. And again, to go from this left side to right side I'm using countable additivity. And this is where the foundations of probability theory comes in. And in here, I have this n. I'm making this the length of this interval. I'm controlling it by this n. So in here, this n really means that I'm breaking this interval into n intervals. And I can take n arbitrarily large, and make the intervals smaller and smaller. And what you should recognize is that this, we can think of it as a Riemann sum. And what I do here is that I write this probability of x as, so what I do is I write this probability x as in here using this limit as n goes to infinity, the probability that's in this interval. So the thing to note is that as this interval is getting smaller and n is getting larger, the preimage is getting smaller. So this probability itself is going to 0 as n goes to infinity, because the interval is getting smaller, so there's going to be less probability. So if we consider the probability of each of these terms as n goes to infinity, then it's going to go to 0. But what we do is we multiply this times n over b minus a, and this is going to infinity, and this is going to 0, and in the limit, if they go to 0 and to infinity at a specific rate, then we're going to get a function f sub x of x, and this is called a probability density function. And this is a density because it's really you can think of this as a mass per unit area. And so this is going to be a density function, a probability density function, and we can take this limit. So in here, if we want to get this type of term, then we have to multiply this, which is this term, by b minus a. So in here, you can see that if you do f of x times b minus a, so bring this over here, then we obtain this term, which is this term. So in the limit for n large enough, then we have that this sum of probability of small intervals turns into this sum. And here, this is where really you should see the Riemann sum. And by taking n to infinity, we see that this is going to be equal to an interval from a to b. And that the probability of x is going to be the induced probability function, or the probability distribution, is going to be given by an interval of some function f of x, which we call the probability density. And with continuous random variables, instead of giving you a probability distribution, the p sub x, you're going to be giving a probability density. And we additionally require for this probability density, so that the whole probability, of all the outcomes, x dx is equal to 1. Implicitly, we already have the countable additivity, and then we actually require for a probability density function to satisfy this condition. And I guess additionally, we have the f of x is greater than or equal to 0. And here we don't have that f of x, the probability density is bounded by 1. It could potentially go to infinity. So we have these two conditions for the probability density function. Now let's look at some quick examples for the continuous case. Or in the continuous case, let me just recap what we did. We have the original outcome space, and we map to the real line, and we want to determine the probability function of the probability of this interval AB. And what we do is we break it up into smaller intervals, and we're going to obtain a probability density function, which is just going to be some positive function, which is not necessarily bounded. And then to compute the probability that x is in A, the probability density, then it's going to be given as the interval of this density function over the region A. And this is how we compute probabilities for continuous random variables. So now let's go through some examples. The first example is the uniform distribution, and this kind of generalizes the uniform distribution in the discrete case. And here I'm dropping my G's a little bit. My solder accent is coming out. Choosing a number x. The interpretation here is that x is choosing a number from A to B where each number is equally likely. So in here, the probability distribution function is just going to be the step function. And it's just going to be flat, and then it's going to step, and here. And it's zero otherwise. It makes sense that it's zero otherwise because there's zero probability of picking a number outside that region. And then inside the region, every number is equally likely. So that means that the density has to be the same throughout. And so we know it has to be flat. And since we have that the sum of all the probability of the whole probability density has to equal to 1, then this forces the height of this block to be 1 over b minus a, so that the total probability adds up to 1. So that's the uniform density. We have now the exponential distribution, which is denoted by this. It has one parameter, and this is similar to the coin flip, getting the first heads in k coin flips. But this is a certain continuous limit of that discrete random variable, where in here you take a bias coin and you decrease the probability of heads. So you make it arbitrarily close to 0, and when the probability of heads is really low, then it's going to take you a lot of coin flips to actually get that first head. So you're going to be flipping that coin for a long time. And if you flip it every second, it's going to take forever to do it. And the way that you can get your first head faster is if you start flipping faster. So in here, this is a continuous limit where the probability of getting heads is going to 0, meaning that it's going to take you more coin flips. But to counteract that effect, you actually start flipping your coins faster, and it's going to be infinitely faster, so that you actually arrive at the first heads within a finite amount of time. And since you're flipping much faster, then it's going to be any number in the real line. So this is going to be the interpretation of the exponential random variable, and the distribution is given by this. And this kind of explanation or interpretation of the exponential random variable is kind of encoded in this statement, where you take your random variable with geometric distribution epsilon. Again, epsilon is a parameter that tells you the probability of heads, and you denote it G sub epsilon, and then you take epsilon goes to 0, and here you take epsilon goes to 0, and this is going to be the number of heads it takes, and then you scale it by epsilon over lambda, which is going to tell you how fast you're flipping the coins, and then it's going to give you this random variable. But it's going to be the distribution, the probability density function is going to be this, and it's only going to be positive in this region and 0 in this region. And let's see, we have this one last distribution. But actually, before I move on to that one, let me uh, add an additional note that this exponential random variables has a memoryless property. Memoryless property. So if we go back to the geometric random variable, is this interpretation of flipping a coin until you get a heads. And in this discrete case, this memoryless property really means that if you flip a tails, it doesn't make it more likely that your next coin flip for the heads to get heads. It's still equally likely to get heads or tails. So it doesn't really matter what happens in the past. Your next coin flip is still independent of that, and you can wait just as long. So it doesn't, excuse me, it doesn't really affect your waiting time for the next heads. And here, this memoryless property carries to the exponential random variable. And you can think of this exponential random variable as a random waiting time for an event to happen, meaning the head to land the heads. But we have this memoryless property, meaning that it's the amount of time that you wait is independent of the amount of time that you've already waited. And this is an important property that essentially pins down this distribution. Excuse me. Let's drink some coffee. Much better. So if you just require this memoryless property, you pretty much get this distribution. And you have this parameter lambda, which essentially tells you roughly how much you're going to wait for this random event. But you can think of it in terms of the geometric distribution. Now, this last distribution, x, it has Gaussian distribution. Also, people call it the normal distribution. Is ubiquitous to probability theory. It appears everywhere. And here, I'm just keeping one parameter. You can add another parameter, which is the center of it. But in here, we'll just add the sigma. And really, the interpretation of this random variable, if we go to the coin flip example, it really is telling you that it's accounting for the fluctuation of the number of heads in infinite coin flips. And this is the distribution function. And in here, if we take the binomial distribution, we said that the notation is going to be just a b and p. And you take the binomial distribution with np, and sigma is equal to this. Then after n coin flips, you can actually compute using expected values or intuition. After n coin flips, you should expect np number of heads. So if you subtract this from the binomial distribution, you should get a number that is going to tell you how far you're away from the expected number of coin flips. And this number is actually, as n goes to infinity, this number is actually going to go towards infinity. So the fluctuation is going to be as you do more coin flips, you should expect the fluctuations around the expected number of heads to actually be fairly large, because as you have more trials, more coin flips, you should expect more time, more space to have weird things to happen. So the fluctuations are going to get larger and larger just due to the nature of, like, you have a lot of coin flips. So things are going to get out of hand. But we can scale this. This is going to infinity, but we can control how large these fluctuations are, and they're going to be on the scale of square root of n. And if you look at this limit, you actually get this random variable, the Gaussian random variable, or the normal distribution, and you're going to have this distribution be given by this, where omega is, sigma is greater than 0. And And here, this type of limiting process happens for a lot of random variables where you end up with this, and this is the content of the central limit theorem, but that's not very important right now. This is just this uniform distribution, or I mean, rather the normal distribution. The Gaussian distribution is ubiquitous to probability theory and appears in a lot of places. So this is the end of this lecture. Random variables. The next lecture will be expected value. So this is where we start getting more information about random variables. And one last thing before we leave, you'll note that a lot of this probability densities, they're like in certain regions they're zero, and certain regions they're not zero. So in the region where they're not equal to zero, this is called the support of the random variable, meaning that these are the possible values that the random variable can take. And here the support is the whole real line. It could be anything. Here the support is just the positive numbers, and here the support is A to B. And this is some terminology that may appear here and there, but it's not crucial. But anyway, this is the end of this lecture. Thanks for tuning in. I'll see you in the next lecture.